So we will start now. So before I start, just wanted to check how do you find it, the whole concepts and everything. Is it a lot of things are new to you, or there are a few things you already know?
Interesting.
So some new things, yeah. Yeah. So we keep doing things in daily life, but sometimes we are not aware, right? Some of the things are very kind of prone to attacks, yeah, and we feel it's safe, but not always, yeah. So it's always good practice to know how things can go wrong, so you are more prepared, yeah. So you are more proactive rather than always when something happens then go on to fix it, okay. So it's better to always do extra cares, yeah, so that things doesn't go very wrong, okay. So last time we covered this briefly, yeah, you remember, like how we can detect prompt injection attack. So this is something very interesting to all the companies who are developing large language models, yeah, to define their criteria, like when they should not give any answer to the users, okay. So you tried the prompt a different way, but it's not directly going to find an answer, yeah. This prompt is first analyzed, yeah, and then after analysis it may say, okay, sorry, I cannot answer, yeah. There is no need to go into the whole network to really find out the answer, okay. Yeah. Some of the details we already discussed, but this is some more experimental setup, you can say, yeah. So the data set we used, it has 5,000 labeled samples. So it has some 5,000 prompts basically, and some are malicious and some are non-malicious, okay. And you can find this one online, it's available, yeah. So it's called safeguard prompt injection, okay. And for the execution environment, Google Colab was used. I don't know if anyone of you use Google Colab. Any programming you want to do, it has nice set of libraries, yeah. So you can use it. And these are some hyperparameter details, yeah. Number of epochs, like how much training you want to do. So there should be a stopping point, yeah, otherwise it can go forever. And these are the some libraries used, yeah. You might have heard, if you want to do anything with AI, PyTorch, or there are lots of other, yeah, from different companies, you can use this. Now this is the accuracy result. So there are different models, and this is the one we proposed, yeah, the one you saw, the workflow. And these are some existing approaches, yeah, logistic regression, XGBoost, random forest. So these are also very popular, yeah, those three. So if we look the accuracy of everything, so we are getting a bit better accuracy in comparison to those. And you know, when we are dealing with some models, we always want accuracy close to 100%, but it's never. That means if it's close to 95 or more than 95, it's better, yeah. So you can see we are getting very high accuracy. But like I said, if you get in something, typically you pay in something else, yeah. But if you look the training time for our approach, it's a lot, yeah. So logistic regression, it's just regression modeling, yeah, it can be in fraction of seconds. XGBoost and random forest, they are in like 4 or 5 seconds, but our approach takes 40 seconds to train, yeah. Again, for inference, you can see those approaches are taking much less time. These are the milliseconds, and ours take around 1.4 milliseconds. So you can say we are kind of trading off training time or inference time with the accuracy that we are getting, okay. So there is always a trade-off, okay. Yeah. Okay, so again, I think this one you may find relaxing and interesting. So this was one of the attacks on AI models, right? Prompt injection attack. So with this, I wanted to check, can you think of other attacks that can happen on AI models? So let me try that slide, I mean that web page, yeah. Look at this one. It does not work from there, so we have to try from here. Let's check, maybe it works. No. So typically I don't need to change anything, just in the slide it works. So not, so go here. Okay, if we look the web, I think it should be there. The thing is, if you are working on AI and little bit on security of them, you may have heard something. Okay, data poisoning, yeah, that's one very interesting attack, and there is a lot of research on it. So, you know, all the AI models are trained with some data, right? And then data poisoning is like you make some extra data from yourself, but that data has some kind of malicious contents. So you train the same model again with this data. So after it is trained, if someone tries to get an answer, it's not going to give, basically if it's kind of a classification, it may give you wrong answers, yeah. So for example, some of the attacks that had been done, it's about like kind of a speed limit on the traffic roads, right? Sometimes it's like 60, 70, 80, or sometimes this is stop sign, yeah. So let's say if your car is driving and someone, if AI model is doing that recognition, yeah, if it is trained with some malicious data by adding some noises in the data, then it may say this is not a stop, yeah. In place of 60, it may say it doesn't recognize, or it might be some different speed. Maybe 6, it can read 8, 80, yeah. So these kind of things can happen. Yeah, so jailbreaking is another thing, like basically you kind of go and change something in the model, yeah. And it can be anything again, something with the data, something with the model, yeah. Upload malicious file in AI model, it is more or less the same, yeah. So you train it with some malicious contents, yeah. File could be image or some text, whatever, yeah. Okay. Imagine all the chat bots, yeah, that we have, this chat GPT or Gemini or from Meta, yeah, all of them. If you get access, you can train it with some data, right? And then it may give some kind of response that those companies don't want, yeah. So that is why these models are very, very closed, yeah. There are some open source one, so you can take that, you can make them malicious, but not all of them are open source, yeah. Okay, good. So those are some nice examples, and you know about them. Okay, so this is what I have listed here. Data poisoning, you already know. Model poisoning, some of you said jailbreaking, yeah, that can be form of model poisoning. So it's like each model has a lot of parameters, yeah, there are nodes, connections, so it's recording each node there are parameters, yeah. Someone can replace the parameter, yeah. So if you can get the access of the model, which means you are getting also the access of the parameters, you simply replace the parameters, then model is going to classify some very differently, or it's going to do something else, yeah. There could be some other thing. So like these days you can see we are using lots of open source codes, yeah. Now we are using open source AI models as well, but these open source places there is not any kind of verifications, yeah. So for but if you consider other places, like you download your apps, right, from Google Play Store, so Google is doing nice checking whoever is uploading an app there, other companies as well, but lots of open source places there is no checking, yeah. So what you could do, you can take an open source model and you could do some changes in the code, yeah, and then upload it again. And this is this, it can be something that is going to spoil the responses of the model, yeah. And then basically it's kind of attack on the AI model, yeah. So attack here doesn't mean like you are going to steal some sensitive information. In a sense, it could be like a denial of service, yeah. So whatever someone expects from the model, it's that person is not getting that, okay. So these are the some other attacks, I would say, one can think of. There may be more, yeah, but these are the some. Oh, okay. Taking data from known sources and not open source sources, yeah, that's good idea. So you basically do things from trusted places, yeah, not just take from anywhere, yeah. Yeah, that's one nice idea. Anything else anyone can think of? Impose access control, yeah, that's one I was going to say in a bit, but nice to see someone has already said. So basically you don't let maybe your model get accessed by anyone, yeah, it's kind of a closed model, yeah. So if it is closed model, someone gets the model, you can put like even ID password or something like that, yeah, and you can allow like nobody can further train the model. It's just whatever it is doing, it will do that. And data validation across the fields, okay, that's interesting. So maybe it's about whatever data, extra one, you want to use to train it further, but it is malicious, so that data can be validated, yeah. There could be maybe some filter or some mechanisms before putting it to the AI model to make it basically poisonous. You can have some validation like how valid, I mean, or if there is anything wrong with the data. If wrong, remove that particular data, yeah. But it can be very difficult job, yeah, not easy. Okay, I think you have nice ideas how to basically stop it. Okay, good. Let me see, I think with this I had a next question. No, this one we have done. Okay, the next one about model poisoning. How do you think we can stop the model poisoning attack? So some of the things you said it's already applicable, yeah, access control, yeah. Anything else? Black box models, yeah, I think, yeah, that's good. So basically nobody can take it, yeah, it's like a black box, you are never going to get access to it, yeah, or you can never jailbreak it, yeah. So it's closed, you can't really get access of the parameters, yeah, so you can't change it. And there are a lot of models like that, right? The one we use, these popular ones, we can never get access of those, yeah. There was a time like, you know, everybody started training their own large language models, but then there was also a noise like if one company can share the parameters with others, they don't really need to train. Because everybody is training, like, and this training happens on thousands of servers and over like 6 months or 9 months, yeah, this kind of infrastructure is needed, and and the power is needed, yeah. So it's not good for sustainability. So some people raised like if this can be shared, but companies have to make profit, yeah, so they don't want to share. So that is why this kind of thing happened, yeah. So it's kind of a black box under those companies' environment, yeah. Okay, I think that's one nice idea. You don't let anybody access the parameters somehow, yeah. Okay. Access control again can be applied, yeah, like in the previous one, not let anybody access it, yeah. Okay, good. there was third one. Remember I said someone can take the open source code, can do some code re-engineering, can then insert some malicious activities. So how do you think that one can be stopped? So the same thing can be applied, yeah, access control or making it black box. But now I'm saying imagine you get the access, yeah, and then what can be done? Yeah, that's interesting. So it's like if you change something, you want to put it back on the open source platform, you can have some thorough security audit for all code commits. This is what these smartphone companies are doing, yeah. Like if you go Apple Play Store or Google Play Store, Apple, so they basically, you can't just put simply there, yeah. If you kind of put a request, they have a thorough checking. Maybe it's automatic, but if something goes wrong, they send you some kind of email or something, this needs to be changed because they have some security concern. So something like that, yeah. Yeah, but again this needs a lot of manpower, right? So companies may be not willing to do it, yeah, but this is nice idea, yeah. Okay. So I can think some, okay, so restricted access to only few developers, yeah, you can, yeah, who are trusted basically, you can always try to give access only to those. So in again along the lines of security audits, yeah, so you know you can perform some kind of analysis on the code, yeah. So it's like there was already a model or this set of codes, yeah, you took it, changed something, yeah, but the one you took, so there could be some mechanisms just to check this is already fine, yeah. Like at the moment you take some executable or something, you try to install into your computer, yeah, but there is some antivirus that checks whether this executable is fine or not, or this application is fine. Similarly, you can have some kind of some checking mechanism, take the code, check it if everything is fine, yeah, and then only basically you let it upload. So there are some people have developed some mechanisms for checking executables, yeah, to kind of find out if there is any problem in that, yeah, and that's what exactly is lots of you can say antivirus things do, okay. So it's some kind of analysis of the code and then coming to some decision based on that, okay. Good. Okay, let's go to the slides now. We did this, we did this. Okay, any questions on this one? No? So with this we have covered basically everything about security, yeah. Now whatever time we have left, we will cover the remaining topics, yeah, sustainability and security together, and we will look what are some emerging trends that we should be typically focusing on in the near future, okay. Okay, so now, oops. So this will be part of these lectures, yeah, 7, 8, 9 and 10, although for 9 we have partly covered, yeah. So we will focus on sustainability, methodologies and analyzing them and jointly considering sustainability, security, and then like I said we will be looking some emerging trends. So one way to achieve sustainability is basically by doing intelligent computing. So intelligent computing simply means you apply some intelligence and try to achieve whatever you want. So for sustainability we have mainly two goals. Yeah, one is when you are doing the computation or something is running, for example this PowerPoint on my laptop, you should take as minimum power as possible. So the hardware should take as minimum power as possible. Yeah, so energy efficiency or power is one thing. Another thing is, let's say if this PowerPoint is running, it might be it's heating my laptop a lot. Yeah, if and then I'm forced to replace, so there is like kind of electronic waste. Yeah, so if you can increase the things are made, first that impacts the energy efficiency and second that impacts the waste as possible. Again this is about computing, but there are some other branch of research kind of true when we get these electronics, yeah, in our hand and then we start using it. Yeah, so when we start using, but there is a huge amount of power that is already wasted in producing it. So if you take % power is already wasted, so you use it for next 4-5 years. Yeah, but by the time you get, then this is manufactured in a kind of very high temperature environment and it takes a lot of power there. It's already been wasted. Yeah, that is why you can say increasing the lifetime is even more important. Yeah, then basically these you can say carbon impact activities can be done. Yeah, okay. So we will not cover something that what can be done after we get the electronics. Yeah, and that is part of intelligent computing. Okay. So we already have looked at the devices at various scales. Yeah, you remember there was a devices and cloud. Okay, so I'm just putting this picture again. Yeah, so we can have devices at various, some when we are traveling, and there could be some, yeah, like car when we are traveling, and there could be data centers as well. Yeah.
What is the difference between edge and fog devices?
So I think edge is typically that we are surrounded with kind of intermediate layer between the edge and the cloud. So it's like, yeah, so first we try to do everything on the edge. If it's still like there is a performance bottleneck, then you can send to cloud. Okay, so those electronic devices, yeah, by these kind of platforms, yeah, multi-core platforms. So this one you can see that is used in servers or data centers. Yeah, on the top right you can see this is a board called Odroid XU3. Yeah, so that has 8 big cores, 8 big little cores. These are big cores, these are little. In kind of appearance also their size is different. Yeah, so it's like one big can accommodate 4 little. So later on we are going to see where exactly this was used, and there are from different companies also, right? From NVIDIA, you know, they have this Jetson series of boards. Yeah, so like some GPUs and some CPUs. Okay, there are other companies also, they are trying to integrate all different kinds of processing elements. Yeah, so these are the kind of hardware or processors that are powering up devices at all scales. Yeah, it can be embedded, fog or cloud. And if you look all of these devices, yeah, you can see these three are kind of heterogeneous, yeah. So this one you can see like all the processing elements or all the cores are of the same type, but this one has different kinds of processing elements, yeah. That is why we say heterogeneous, yeah, like two kinds of CPUs and GPU. So CPU and GPU, and here is like CPU, FPGA, and another 16 core processor, okay. So now if we look the one that was on top right, yeah, so that one was actually used in Samsung Galaxy S3 mobile phone. And if you look any smartphone now, the architecture is more or less the same. It's just at that time the big was Cortex A15, now big may be Cortex A75 or something. It has become more powerful, and little has become more powerful, yeah. And there is always some GPU. So almost all the smartphones are using similar architecture. So the same chip that was in Samsung Galaxy S3 mobile phone came with some development board as well. So this board is called Odroid, I said earlier, and the chip name is basically this Samsung Exynos 5422 system on chip. So you can say at the end, this is the chip name that Samsung gave it to its products, but it used some processors like Cortex A15 and Cortex A7, but those processors are made by different company, yeah, it's from ARM. So they take it, like they pay for each of them, they manufacture the whole chip themselves, yeah. That's what they do. This big little we already have said. So you saw like there is some heterogeneity, right? There are some big cores, some little cores. So there is some reason to do that, yeah. Why not just have only same type of cores, yeah? So I have put a question here. So what if there is no heterogeneity in terms of processing capability of the cores? So do you think there will be no impact? You can put all homogeneous, or it can impact performance. Maybe I don't need to put that one, yeah, you can simply just talk here. So which one you think is true? Will there be no impact? It will get impact, right? So you know, typically heterogeneity is for a reason, yeah. So the big cores, like I said, one big core, the size of it has like four little cores can come, yeah. So let's say in the phone you are doing lots of things and some more compute intensive processes, then you need the big cores, yeah. But there could be times you basically are not doing lots of things. For example, my phone is sitting idle, yeah. So there could be, everything can be migrated to one of the little cores because that will take very less power, yeah. So basically depending upon the situation or the workload in the system, you have the flexibility to switch from one place to another to save the power, okay. So this big little simply came to basically save power so that the battery of the smartphone can last for a long time. But think like similar approach can be taken anywhere else as well, yeah, like designing the new CPU, designing the new GPU. That is why you say these days anything comes with it doesn't have just the GPU, it doesn't have just the CPU, it has like mixture of both CPUs, GPUs, also some kind of specific processing elements as well, yeah. In the phone these days there is another kind of processing element, it's called NPU, it's like network processing unit, yeah, or neural processing unit. So that does nice job for some AI workloads, yeah. So there you can imagine now there will be a manager that's going to decide what's going to run, and it's going to decide what kind of processing element has to be used, okay. Okay, I'm trying to go to the next slide. Okay. Okay. So I think we already have discussed if you have heterogeneous components in your processor, how you can basically make a use of them to save energy, but that is applicable everywhere, yeah. For example, let's consider the workload of an organization, yeah. So it's like this whole IIT Guwahati is a processor, yeah, but the people working and doing anything, they are workload, yeah. So some of you could be mathematicians, some of you could be computer scientists, coding, and there are lots of admin people, security people, and all those, yeah. So basically these are different kind of workloads, right? And there will be different kinds of employees as well to handle that workload, yeah, like heterogeneous, yeah. So basically if this is there is a coding job, if you give that to basically some HR personnel, imagine what will happen, yeah. So you need different kind of employees, yeah. Just like then these are different kinds of processors that are suitable for different kinds of jobs, okay. That is why heterogeneity is important, yeah. So this is how you can allocate different kinds of jobs to the most suitable processor or most suitable person who can do it best, okay. So like we said, the most important thing is to kind of find out what kind of tasks to give to what person, yeah. So that kind of things are also called like some kind of knobs or controls, yeah. So let's say now we want to optimize something, right? If you are doing that, there is some purpose, right? Either to reduce the cost, reduce the energy consumption, or maybe something else, yeah. So the kind of controls we are doing, that is called like knobs or control, and we typically can refer that like optimization knobs and controls. Now if we go back to the processor context, we are going to look like what kind of all possible knobs and controls we can have, okay. So the first one we can say is kind of mapping, yeah. So it's basically kind of identifying for an application what are the cores that will be used, yeah, because in each platform these days, you saw the platforms, right? They are like 60 cores, 10 cores. Which are the cores that are going to be used? So kind of mapping the tasks on the cores. So that is one of the knobs, yeah, and this is one example, yeah. So it's like if in your platform there are lots of processing elements, so you can put some task on some cores and then you can establish the connections, okay. So here like these 4 cores are used, okay. So this is one option, yeah, but you can map, basically you can use any combination. You can use 1 core, you can use 2 core, you can use 3, and out of like 3 you can decide these 3, you can decide these 3, so many possibilities, yeah. So mapping is one of the knobs or controls if you want to optimize something, and if you are doing all those mapping options, you know the results will be different for the timing, like how much time the whole application will take to execute and how much energy it will consume, yeah. Similarly it will apply at a lot of places, yeah. Let's say in the data center there are a lot of servers, right? If there is a request coming from outside, it depends on which server, in which way you are using the basically the processors, it will have different power consumption, okay. So mapping is one of the knobs, I would say, yeah. So we already have seen what it does. It defines the assignment of the task and also it defines the ordering of the task. When ordering comes into picture, let's say on one of the core there is more than one task, right, and processor will be given to only one of them at one time, right. So ordering is basically which one will be first, which one will be after, which one will be next, or it could also be in a round robin fashion, yeah. So for example in our laptop there are a lot of applications running, right. So there is an ordering defined, most of the time it is kind of a round robin fashion. Each of the processes are given time, yeah, few cycles, few cycles, few cycles. That's why everything is running together, okay. Similarly ordering has to be defined here, but mapping is part of both, yeah, finding the location, and if at one location there is more than one activity, which one will happen first, which one will happen second, okay. Another one is DVFS dynamic voltage and frequency scaling. Yeah, we already have seen it. Yeah. So just to mention, this is supported in many advanced processors, even in the laptop or smartphones it is there. Okay. So just to brief what it does. So let's say we have this 3 core platform. Yeah. So there will be a controller attached to each processor. Yeah. It's going to basically define if you can run this processor at high voltage and frequency or low voltage and frequency, and that typically you define based on how much workload is there. Yeah. This is again, you can say, to save the power. Yeah. So we can look the example. Yeah, how this can be used for energy savings. Yeah. Let's say you want to execute some task, right, and if you are running at the maximum frequency, your energy consumption will be very high from the very start, right. You might have you might remember the equation, how the power is defined. Yeah. So it's like dynamic power is C voltage square into F. Yeah. So if F is high, so it's not like voltage will be the same. If F is high, voltage will also be high. There is corresponding kind of pair, voltage frequency pair. So things will consume lot of power, but it can finish fast. Yeah. But if there is some application like the deadline is far away, yeah, then basically you don't need to run that fast. You don't need to complete this quickly. Yeah. So you can run at some lower frequency, maybe whatever is maximum, half of that, and then you can take all the time. But if you now compute the overall energy, it might be lower. Yeah. Because every moment you are dissipating or you are taking less power. Okay. So that's the use of DVFS. Another examples could be even if there is no deadline. Yeah. So if my like this Teams is running, yeah, or this PowerPoint is running, there is no need to run the processor at very high frequency, but you can't also run at the very low. Yeah. Otherwise things can be very slow. So you just have to find the right balance so that you just deliver the performance that is needed, but at the same time you also save energy. Yeah. So my battery can last for a long time, and if this task is running in a data center, again you can save some energy bills. Yeah. Okay. So we saw mapping is one of the knobs, and then DVFS is another knob by which we can control energy consumption. Yeah. Another thing, again very popular, and it has been in lots of processors from a long time, is called dynamic power management. Yeah. What it does, it basically shut down processing elements when inactive. Yeah. So if basically something like a processor was doing something, but maybe after certain point there is no load to process. Yeah. So what it can do, it can shut it down to save the power, right. Again, to shut down the processing elements, there could be two approaches. One could be greedy, another could be timeout approach. So greedy means like the name says, right, do it as soon as possible. So as soon as processing is finished, go to the sleep. Yeah. And lots of actually in our laptop we can do that. Yeah. You can define the time when you want the laptop to go to sleep if there is no activity. Yeah. No activity means there is no processing, so it can go to sleep. Yeah. And another one could be timeout. Yeah. Again, this one we do in our laptop, right. We set a time. So even if there is no workload, we stay active until certain point, and then we go basically the sleep mode. Yeah. So these are the ways basically to save the power. Okay. And again the same can be applied everywhere. Yeah. Okay. Now I have a question. Which approach you think is better, the greedy one or the timeout? Okay, I will throw that slide, not this one. We have done this one. Okay, here. So do you think greedy is better or timeout is better? Timeout is something that we have in our laptops, right? You can say go to sleep after this time, that time, yeah. Okay, good to see there are people on both, yeah.
Depending on the application, what kind of application we are using.
Interesting, yeah. Yeah, so I would say it depends on the situation. Sometimes greedy can be better, sometimes timeout can be better. But there is a reason for it, yeah. So what it is doing, so it's running at high frequency, you can say, then processor finds there is no workload, yeah, then it goes to sleep mode, yeah. Greedy is going to sleep as soon as there is no workload, yeah. But if you go in the sleep mode, to come again into the normal active mode, it takes time and it takes power, yeah. So for example, even the laptop, right, there is like hibernate and all those kind of modes and shutdown, yeah. So it depends where you are, and then it takes more time to come, yeah. It's like a hill, yeah. If you go more down, it will take more time to come up. So if you have gone sleep, yeah, and let's say we did greedy approach, maybe just after 1 second a workload came in, yeah, and it needs to be executed, but then it will not be immediately executed because the processor has to come to a normal working stage. So the workload will have to be waiting, yeah. So there will be penalty in performance, yeah. Okay. Whereas if it's timeout, maybe you waited like 5 seconds. If this workload came just after 1 second when nothing was like the previous one finished, then basically it will pick, yeah. There's no need to come again from the very idle or sleepy stage to this one, okay. So again it depends. If it's very kind of a dynamic situation where the workload may come at any time and can go any time, so in that case I would say greedy is not the best, yeah. You can kind of think of, okay, if there is no workload after maybe 5 minutes, it is expected there will be nothing, yeah. So but yeah, so in that kind of fashion, okay, yeah. So it's like you said, depends on the situation, yeah. So one can perform better than other, so it depends where exactly it's being applied. Okay, it's slow. I think when I'm on this kind of slide, it takes time. Okay, so we saw basically two controls, DVFS, mapping, yeah. The third one we can think of is kind of partitioning, yeah. So typically you have kind of this kind of workload, yeah. The applications are represented typically as data parallel, so that means like there can be many processes that can be happening at the same time. So let's say this is representative of one applications, yeah, and each of these elements are called work items, yeah. If you go to GPU programming, this is how it happens, yeah. So work items are called like in OpenCL programming language, that's for GPU. So if for an application you have this many work items, now if you have a platform that has both CPU and GPU, right, then you have a job to kind of identify what fraction of work items will go on the CPU and what fraction of work items will go on the GPU, right. So again you can see here there are so many possibilities, yeah, but this partitioning is another basically control, yeah, or knob. So you can define several partitions and each of them are going to give you different energy consumptions and different performance, okay. So here this is one, just an example, yeah. This is one you can do, so like 0.60% of the workload or 60% of the work items on the GPU and 40% on the CPU, Yeah. So we have seen three of them. Yeah. Mapping, like what cores do you use, and if on a core there are more than one task, in which order they will execute, and then DVFS is another control. Third one is partitioning. Okay. I think we will take like 5 minutes break and then we start again. Yeah. It's not a proper break time, but just 5 minutes to relax a little bit. Okay. And later on we are going to see use of these. Yeah. So in my research group, what we did with these kind of ideas. Okay. So how much energy we saved. Okay.
Kind of partitioning and mapping comes together now. First we do partition and then we map की कौन सा वाला block जो है उसका execute करेगा.
I think these all three can come together. Yeah. So because some architectures are like there is a cluster of CPU. Yeah, I said there is another cluster of CPU, another cluster of CPU. So first there is hierarchy, right? You have to define like, okay, how much workload goes on this cluster, and then within the cluster how do you partition, and even if you partition, how, at what voltage and frequency you run those different cores. So there are so many possibilities. Yeah. So that is why if you apply kind of some reinforcement learning or something in these situations, it's never best. That is why you can't find any reinforcement learning or AI based approach in the smartphones. Yeah, because the possibilities are so huge, it's not going to give you the best results. Yeah. Okay.
And so what kind of factors will decide the partition?
So I think it depends what you want to achieve, what's your aim. Yeah. If it's timing, you may define like maybe half. If it's energy consumption, maybe this way. In a bit we are going to look basically, if you partition in different way, what is the impact on energy, what is the impact on performance. So then you can decide like what exactly you want to achieve. If you want low energy, you choose this kind of partitioning. If you want high performance, you choose this kind of partitioning. Yeah.
In the performance, it will include latency, throughput.
It's mainly latency and timing. Yeah. Latency, timing, throughput. Yes. Okay.